Hey, welcome back. Today we're going to be talking about how you can figure out where an earthquake was centered or where the epicenter was using P and S waves. So I'm going to talk you through what P and S waves are. This is appropriate for a geology or a physics or even a physical science class and trying to figure out where exactly epicenters are for earthquakes. And this is important because earthquakes do tremendous damage and they can be really scary if you're in the middle of an earthquake. Alright, so let's go ahead and get to it. First of all, I do need to talk about an unrelated phenomenon, but it's going to form a perfect analogy for something for later. I need to talk about lightning and thunder. The reason will become clear later, but essentially what you need to know is that lightning and thunder are two phenomena that are from the same event. So generally lightning happens, that is a flash of light, so that wave energy is spreading out using light, and then we hear the sounds of the thunder sometime after. Now there's a difference in time between when the light strikes our eyes and the thunder strikes our ears, and the longer the difference in the time between seeing the light and hearing the sound tells us how far away that event was. So if there's a long time, like maybe 7 seconds, say, in between the light flash and the sounds, you know that lightning strike was relatively far away. And if the difference in time between the light flashing and the sound hitting our ears is relatively small, that means the event was actually very close to us. So why am I talking about lightning in the context of an earthquake? And that's because we're going to use the same idea in talking about earthquakes. So let's do that. So it turns out that there are two different types of waves that both come from an earthquake. They are called P and S waves. When we talk about P waves, they're also called compressional or longitudinal waves. Sound is a good example of a P wave. Whereas S waves are also called transverse waves. And P here stands for primary. This is the first wave that a seismograph station records data from. And the S wave stands for secondary. This is the second or slower wave that hits a seismograph station and we get data about an earthquake. This you will get in the context of a waves unit in a physics class if you're taking a physics class, but you could say one major difference here is if you compare the direction of the wave itself, that's going from left to right in both of these animations, but it turns out that the medium is the thing through which the wave is traveling. That's going to be going in the same plane as the direction of the wave itself for a P wave or for a longitudinal wave, you could say. Whereas over here on the right side, the direction of the wave is from left to right, but the direction of the medium, the motion of the medium, I should say, is going to be at right angles to the direction of the wave itself. You may have done this at a sporting event. If you ever do the wave, you stand up and sit down and you're moving in the up and down axis. The wave travels the length of the stadium in the x-axis, so to speak. Those are at right angles to each other. So in this context, though, we're going to say that the P wave is faster, the S wave is slower. The difference in time is important. That's like the difference in time between light and sound coming from lightning. We can tell how far away the event was by the difference in time that we get from the P wave and the S wave. Alright, so taking that information, I do want to point out quickly how a seismometer works. So imagine for a moment that you have something very massive right here. As the ground moves from underneath, if this is a rolling disc of paper, then with this being very, very massive, it's not going to move very much because it has a fair amount of inertia. Inertia is the tendency for something to stay at rest if it's at rest, or to stay in motion if it's in motion, and it's related to mass. The more mass something has, the more inertia it has. So this is going to remain relatively stationary as the ground shakes, and as the ground shakes in this plane right here, and the paper is rolling in this plane right here, we can get a record of that shaking. And so that's our seismograph right here, and based on that data, we can do some calculations of where the earthquake actually was. So to demonstrate this, let's say we do the calculations, and I've got a screencast where I show how to do those calculations. I'll put a link up to that later in this screencast, but what I will say now is that let's imagine we have a seismograph station in Los Angeles, and it turns out that it's a certain distance away, so we can effectively get some distance. So like maybe this red dot right here, or plotted on this map, it's like this red dot right here, or maybe it was this far away, or maybe it was this far away. If you think about what I'm drawing on this overhead map, essentially we know the distance, but we don't know where it was located. So what could you make out of this and be correct if we were trying to determine where the epicenter of the earthquake was? Well, you could actually make a circle out of this and say, well, we know that the earthquake happens a certain distance away from our seismograph station for Los Angeles, but we don't exactly know the direction. And so just based on that, there's no way to know. So what we're going to do is say, well, let's just use this as a circle. We'll get rid of these individual data points because we don't know exactly where it happened, but it happened on that circle. So what could we do next? Any guesses? Well, what we could do next is call up another seismograph station, let's say in Torrance, California. And if we do that, Torrance will give us our data and will help us to figure out where exactly this earthquake has occurred. And again, we don't know exactly in what direction from Torrance it was, but we know the distance. So in effect, we know like a radius from Torrance. So we can draw sort of an overhead circle and think about where this would be. Now, where would the earthquake happen? Well, we don't know exactly where the earthquake would happen, but it would happen either at this intersection point or at this intersection point right here. And so we can go ahead and label those on our map. And so we've narrowed it down, the epicenter of the earthquake, to these 2 points, but we still don't know which one it would be. Any guesses as to what we could do that would help us to completely narrow it down to just 1 point? Well, yeah, we could get data from one last seismograph station. If we did that, like called Anaheim and said, can you give us your data of where this is? Then what we can do is figure out where those 3 circles intersect, and where those 3 circles intersect is considered to be the epicenter of the earthquake, at least on the surface of the earth. So that is called triangulation, and you can kind of figure out where something is going to be based on 3 circles on an overhead map, given the distance in between the event and the recording device. So that's actually really useful information to be able to plot that. And if we do that all over the world, if we plot the major earthquakes that have happened all over the world, you start to see interesting and important patterns. We learn more about earthquakes this way. It turns out that this is not an accident. If you take a look at this, there are a lot of earthquakes that happen in a line or on various points. They don't just happen randomly. They happen very important locations. And it turns out that we know that these are happening all along plate tectonic boundaries, so plate boundaries, when plates are grinding past each other. So this data tells us something very important about the way the Earth works. I do want to say I put a more mathematical based explanation of how we determine the distance in between the seismograph station and the earthquake itself. I'll put a link to that in the upper right about now. And if you have any questions or comments, please let me know down below. And I hope you all have a great day. Take care.